Welcome everybody in the lecture hall. Welcome everybody on Zoom. Welcome everybody watching us from the future. So today we are going to finish what we started last week with cloud storage. That should be actually quite quick. And then we'll move on to the next part of the lecture, which is about distributed file systems, in particular the Hadoop distributed file system. So this is where we left last time. Let you see you that. I told you about the vector clocks that are a clock system that has the property that it's not linear, like a normal clock would just go like a line. But here we have a structure called, you know what it's called, this kind of structure? A graph without cycle? Directed, yes, a DAG, I heard, directed acyclic graph. And so it's a clock system that works with DAGs. Turns out to be the same as special relativity, because in special relativity, we also have this kind of structure in space-time. So it's a bit of a stretch to connect it, but actually it does have to do with that kind of things. There's even a system called the interplanetary file system that is a competitor to HDFS. So there's a bit of science fiction going on as well. But going back to Earth, it's a DAG, it's a distributed acyclic graph, and we have a clock system that increments always in connection with a specific server. So we have server A, node B, node C, and whenever a server touches the value associated with a key, it increments its counter, right? So A makes it 1, then makes it 2, then it's server B because there's maybe a partition or something, and B increases it to 1. Then here, independently somewhere else, C increases it to 1. And then we reconcile later in the common future of B and C. We have A that reconciles the two as again, a unique version, right? So you understand this idea that with eventual consistency, we might have a conflict at some point that gets resolved. Okay, who is with me? All right, I have a whole animation to show you and then we'll be done. But before I do that, I would like to ask you this question to let your memories come back from your mathematics courses or theoretical computer science courses. Which one of the following most generally designates a relation that is transitive, reflexive, and anti-symmetric? Is it a total order, a pre-order, an equivalence relation, or a non-strict partial order? Right. Only with these assumptions, right? No additional assumption. So we have a majority. A lot of you see a non-strict partial order, and you are correct. Congratulations. This is a partial order. But I want to give you the overview of that. So take a mental snapshot of this. That doesn't work. So the effect didn't work. I need to click maybe now. Yeah, now. Okay. So this is how it works. So you have these notions on relations that there can be reflexive, means that an element is in relation with itself. That's reflexive. Transitive means that if A, so I'm going to say smaller than, but that's just the name of whatever relation, like A smaller than B and B smaller than C, then A is smaller than C, right? That's called transitive. Symmetric means that if A is smaller than B, B is smaller than A, but of course you wouldn't call it smaller than in that case, but I mean, you get my point. If it's anti-symmetric, then it means that if A is smaller than B and B is smaller than A, then A equals B, right? In that case, you would call it smaller than or equal to. Of course, if A is smaller than or equal to B and B is smaller than or equal to A, then A equals B, right? So that's anti-symmetric. And so we have a whole catalog of mathematical structures that go with this. So the simplest you can have, well, there's even simpler than that, but let's say a pre-order just assumes reflexivity and transitivity. Then you get a graph that might have a few cycles. Then if you add anti-symmetry right here, you get the vector clocks, the DAGs, right? These structures we are talking about, and eventual consistency. So this is where we are in the lecture. This is what we have. On the other hand, if you don't add anti-symmetry, but you add symmetry, then you get equivalence classes. That's an equivalence relation, and you have something that looks like this, but in fact, you're just creating groups of nodes, right? That's an equivalence relation, and then mathematicians do things that are called quotients, where you just instantiate these groups. Now, if I stay on that side, and on top, I add one more assumption, that two values always compare with each other. It means that if you have two values A and B, then either A is smaller than or equal to B, or B is smaller than or equal to A. If you do that, then you no longer have a DAG, you in fact have a straight line, which is a special kind of DAG, right? But because you added an assumption, now it's specifically a straight line. So the mental connections that I would like you to do in your head is to associate all of these things. When you have a strongly consistent system, the good old systems like relational databases and so on with acid properties, you have a straight line of versions, version 1, version 2, version 3. It never branches off. You just have this straight line. So this is atomic consistency or linear versioning, right? So you can use linear versioning in order to achieve atomic consistency. If in the CAP theorem you drop the C and now you're only eventually consistent, then you have this kind of structure that is a DAG and vector clocks. In terms of versioning systems, just to connect things again to more strongly in your brain, who remembers the times of SVN or a CVS? Who even knows what that is? Okay, these are old systems. They used version numbers. They are version 1, version 2, version 3, and so on, and you had a line like that. Now you have systems like Git, right? In Git, this is what you have. In Git, you can make branches, you can deviate, and so on. And then you don't even use numbers. You use these UUIDs, like these long strings of integers and letters that you copy-paste everywhere, right? So this is more like Git, and this is more like the older versioning system. So just to connect things a little bit. Strongly consistent and eventually consistent. Strongly consistent, straight line. Eventually consistent, we have DAGs and vector clocks. Who is with me? Okay. You also have systems that actually are there, but then that's not as strong as this kind of system. So that's a totally different set of use cases. That then it's called a dependency graph. And the sort of things you can do is much more limited because you can have cycles in the system. In other words, what the cycle means here is that you're not necessarily eventually consistent because you can never resolve. When there is a cycle, you cannot resolve in this way of adding one more element in the future. Here, no eventual consistency, not even that. Okay, but of course, that's totally outside of the scope of the lecture, and only these two are actually relevant to what we are doing. We'll see cases in which we have linear versioning later with HBase, for example. But now, my animation. I'm going to take the example, you remember this ring, where all the keys are hashed to a position on the ring. That's called consistent hashing. And the computers too. And for the computers, we even have virtual tokens, virtual nodes that every computer might get several nodes on the ring. And then we have this rule that when you own a token on the ring, then you're responsible for all the keys that fall in that range, but maybe even more if you have replication. So a replication factor, duplication factor of 3, then you are responsible for the 3 ranges that come before it. Who remembers that? Right? Very good. So I'm going to take 3 as an example. For simplicity, I'm not taking the virtual nodes, I'm taking the actual nodes, right? So it's just to keep the animation simple. So let's imagine that we have an incoming request that asks to associate the key 1, very original name, with the value A. I'm always going to use key 1, no other key, just to keep it simple. So key 1, and I store the value A associated with that key. So what happens when this request arrives? So it connects to some node in the system. Actually, it can be any node. And then you might remember the preference lists, right? So the preference lists basically gives you a number of nodes, ideally n, that are responsible for that key. In that case, n equals 3, right? So we get the list of nodes, and the nodes responsible for the keys are the 3 nodes that follow the key clockwise in the ring. Who agrees with that? Right? I locate the key, I hash the key, I put it on the ring, and I take the next 3 nodes clockwise on the ring. Who agrees? All right, so we do that. So now, this preference list is something that gets computed. It's not stored anywhere, it's computed on the fly. So the computer that receives the request, based on the information it has about which nodes are in the network, it's able to compute that the nodes are N1, N2, N3, right? And since they're all healthy and reachable, then that's it. That's the first 3 nodes clockwise, right? How do the nodes know which other nodes are in the system? There is a protocol called the gossip protocol, and it's a little bit like the way the blockchain propagates. It's a distributed system, peer-to-peer. Whenever a node joins the network or leaves the network, they just talk to each other with the gossip protocol, and so they know which nodes are there and which nodes are not there, and which nodes are healthy and which nodes are not healthy or unreachable. So this is computed based on the information about membership and the ring and the consistent hashing mechanism with this ring. So then the first one in the list is N1. So the client is redirected to N1 in order to implement that request. N1 is responsible for the key. It's absolutely authorized to handle it. And so it's going to store the key, and you remember the vector clocks. It's the first time that it sees this, so it's going to say N1, 1. That's the clock for N1, first time it sees it, and it stores the value associated with the key and the vector clocks. It's always key 1, so I don't put key 1, because it's only that key, but associated with key 1, we have A, plus the vector clock. So it means it was 1 o'clock for N1 when it actually wrote down that value. Then that propagates through the network. So it connects to the other computers and propagates the value. So now the 3 nodes responsible for key 1 all now have a copy of this, and they all know that it was written by N1 at 1 o'clock, his time, their time. Okay, who is with me? Okay. Then, imagine that now I don't have a put request, I have a get request. Somebody wants to see which value is associated with key 1. So again, that goes through the preference list, N1, N2, N3, they're all healthy, so that's good, we have 3 of them. Then we request all the versions from these 3 machines, and we notice, I don't know why I need to click so many times, I did charge it before. Anyway, we see that they are all the same, so we actually all agree on the value A that was seen as 1 o'clock N1's time. All right? So we return always the value A together with the clock, which is called the context. So it's the context 1 o'clock N1's time. Then we have another request that is, again, a put. And now we want to put value B associated with key 1. N1 is still reachable, is still in charge. N2 and N3 are still reachable. So N1 is going to, oh, yes, there's a question. Yeah, we're going to use this. We just need to do small hops. Where is the question? Oh, there, yeah. Goes to, I think we said, like R number of nodes per system. So are they blocking until they receive an OK from each of those? That is absolutely correct. I'm going to repeat to make sure that people on Zoom also know. So indeed, there's 3 parameters, N, R, and W. N is the number of healthy nodes that you want to make a request to. So whenever you read or you write, you contact N nodes, right? In a normal situation, that will be the N node that follow on the ring. But if some of them are unhealthy, then you go further than that, right? You take the first n healthy nodes on the ring. Then you wait for at least R successful results if you get the value. So you wait for R of them. And once you have R of them, then you consider that the request is accomplished, right? And it's blocking until you have R responses that you can return. Does it make sense? Yes? Okay, I wasn't looking anymore at the right place. So yes, R of them. If you write, then it's W. You wait for W confirmations that the request was successfully written. So it's R out of N or W out of N, depending if you read or if you write. Now there's a few tricks. There is a constraint that you might remember that R plus W is greater than N, if you remember from last time. Now, normally, this condition that R plus W is greater than N, intuitively, it means that there is an overlap between the R nodes and the W nodes, right? It's the pigeonhole principle. If you have 10 holes and 11 pigeons, there is at least one hole that has 2 pigeons, right? Or Dirichlet, there's a lot of names for this. So basically, R plus W greater than N forces the reading set and the writing set to overlap. Right? You at least have one intersection between the two. And without entering the details of that, what that normally gives you is strong consistency, the straight line, strong consistency. Okay? Everybody still following? Because of this overlap. But, because we do want to continue to function in case of a network partition, because there's one that will actually happen here, if we stick to that and we just connect to the n nodes that follow on the ring, because the n nodes that follow on the ring should have a copy of the value, then we would be blocked. If there's a network partition, we cannot continue to function, which is why the system is using something called sloppy quorum. So R plus W greater than N, that's called the quorum condition. That's what gives you the strong consistency. But in order to continue to function in case of a network partition, if some of the nodes are unhealthy, we continue to look further on the ring for more nodes until we get N of them. The reason it's sloppy is that when you do that, the nodes that you are going to find further down on the ring might not have a copy of the value, right? Because they're further than N. If let's say N equals 10, 3 of them are unhealthy, so you would only have 7. So you take the 3 that come next on the ring. But these 3 nodes, they never touched this key, right? They are not responsible for that key in any way, so they are new to the system. So this is what we call sloppy. It's sloppy because we continue to function by just continuing to reach out nodes that might not be in contact with not have been in contact with the key on the past. So this is the reason why you don't have strong consistency even though you have R plus W greater than N because of the sloppiness, because you only contact the first N healthy nodes, and if some are unhealthy, you continue to go down the ring. Does that make sense? Did I lose anybody? Who is with me? All right, very good. So another question?
Like in this example with vector clock, looked like we only contacted one node, and that node would intranet its counter in the vector clock, and all other nodes are contacted by the coordinator and just get the replicate of the clock.
That I should clarify indeed in the animation. So to be more exact, we contact N nodes when we write, but we wait for W success, W acknowledgements, right? We contact N and we wait for W acknowledgements. Right? So it is true, maybe I could have done my animation better. What I don't know and that I could clarify is when we reach out to these 10 nodes, I think, but again, I'll check, that it's the first node you contact that takes care of connecting to them, not the client. So the client connects to the coordinator, And then it's the one node that you're connected to that takes care of reaching out to the next N node. Because the client wouldn't know. The client is not part of the gossip protocol. It doesn't know, everything. So it has to connect with the first node in the list, the coordinator, and then it's going to connect to the other ones, right? If you can make a note of that, I will check that this is indeed correct, that on behalf of the client, it is the coordinator node that reaches out to the next nodes. Right, upon verification, right? Okay, any other questions? Yes, I see one there. Maybe the microphone, because then people on Zoom hear you too. That's what it's for. Yeah, go ahead.
In this example, wouldn't N2 and N3 also increase their counter since they're seeing the value for the first time?
We only increase the value of the coordinator, the coordinator nodes.
Okay, got it.
Yeah, in that case. That's also something I could check. You're asking actually very good questions, going more in depth than the past few years. So second thing that I will check is that the vector clock only increases for the coordinator or for all of the nodes that would be involved in reading it, which is also possible. So that second thing, I also come back to you as a verification. You see, I don't know everything. So yeah, I just check. Okay, any other questions? Okay, then I will continue with the animation. So here, N is equal to 3, so we connect to N nodes. Even if R or W are less, because there's no problem, we still get 3 answers for the read and the write, in this case right now. So we successfully read and write. So now you see we put a different value. Now it's 2 o'clock for N1. So we increase the clock right there, and then we store the value right here, and it needs to be propagated to N nodes, so 3 in that case. And it turns out in this case that it succeeds, and we also get confirmations from three nodes in there, right? So that's the replication. Okay. Now we get the value, and again, that's speaking with 3 nodes. Always contact the next N healthy node, so we get 2 values A and B, but we notice that 2 o'clock is after 1 o'clock, so we can just return value B, right? Who agrees with that? All right, 2 o'clock on N1 is in the future of 2 o'clock, of 1 o'clock on N1. Okay, so far, so good. Now, what if we want to write yet another value, C? Now it's going to be 3 o'clock, and we write it on N1, try to propagate, oh, network partition, right? Like in a Hollywood movie, there is suddenly a lot of action going on. Network partition, we are not able to propagate further, right? Let's say, to simplify, that W was 1, right? And that's fine, it's still written on 1 copy, and then maybe later it will replicate. But okay, so it's succeeding. And because of the network partition, it doesn't propagate further. So now, if I get a value, I try to get a value. Imagine that the person who tries to get the value does it from the other side of the partition, so from that side. Now, it's going through the preference list, computes that it's this node, this node, this node, but the first one is not reachable because the request is from the other side of the partition. So this one is unhealthy. So it's going to request here, here, and maybe a third machine, but that machine will not know anything about the key, right? So a third one over there. So we get 2 results over there, and we return this value. It's an old value, right? That I have over here, and so I return B, even though there was a newer value C over there. Who is with me? See? Okay. Then imagine that somebody wants to write a new value D, but on the other side, coming from here. So they want to now write that value. It's just not clicking. Normally, this is supposed to go further 1 slide every time I click. Not sure what's going on. Maybe the device is no longer working properly. Very strange. Now it's completely on strike. Usually it would at least work when I'm close to the computer, but all right. So now, all right, so it worked. So the request, sorry, the write request still comes from that side. So we read the value B at 2 o'clock, and still on that side of the partition, we try to write it as a new value D, and now it's 1 o'clock N2's time, right? So that's the vector clock. Now it's N2 that processed it. So now it's 1 o'clock for N2. And the last seen value for N1 is 2 o'clock. Now, maybe I should click right here instead. So the network partition is gone. The computers can speak with each other again. And the system is functional again. A GET request arrives very quickly after the network partition is gone. So now all nodes are reachable. So N1 is tasked with finding the 3 nodes that come after the value on the ring, after the hash on the ring. And now we have this. Do you agree A and B can go away because C is in the future of A and B, right? Who agrees with that? Right? 1 o'clock, 2 o'clock is before 3 o'clock. But in fact, if we want to do it formally and properly, we need to explicitly build the DAG of the vector clocks. Who agrees that this is the DAG? Right? Very good. So you can see the network partition that led to a branch in the DAG. Right? Now we have a branch. And so there is a name for these leaves in the graph. It's called a maximal element. A maximal element is basically a node in a pre-order, but in the DAG in the present case, that doesn't have any future, right? It's a leaf, so to say. Yes? Maybe we need to transmit this. Yeah, there you go.
Why was the new context not propagated to N3 when we had the new context at N2, the N12, N21? Why was it not propagated down this time?
So let me see. I think these might be artifacts of the animation itself, not reality. Let me see. I'm going back. Yes, absolutely. So indeed, that would also propagate. In fact, that all depends on the configuration on how much you write, right? Because if you consider that W was equal to 1, then we already return when the first write is confirmed, and then it propagates later. And all that means right here is that the request came in before the asynchronous propagation of the fact that it would also successfully be written at other places, right? That's how I would explain it, right? So I hope it helps. It's only an imperfect animation, right? I'm just trying to illustrate what is going on. Okay, but if it had further propagated, then D would of course also appear on N3 right there. Okay, so now we have a DAG. We find the maximal elements, and these are all the conflicting values that are the most current values. A and B, we drop them because they're all in the past of both of them. And that means that we have no other choice but returning these 2 values to the user and saying, okay, this is your problem, right? These are the values, they conflict, deal with it, right? It's just what Git does, right? When you try to pull a branch or something and there's a conflict, Git tells you that's your problem, right? You need to solve the conflicts and then come back and then make a commit, okay? Yes?
Why do these values conflict? Because like, isn't the vector clock like an absolute function? So if we are taking just like, if I assume the vector clock, the number 1 to be sort of a timestamp, we still have a method to resolve this by like 3 is obviously greater than 1 and 2.
Mm-hmm.
So we can assume that, yeah, the last 3 was made the last update was made much later at a much later timestamp than 1 when N2 made it. So why can't we just return C?
For the same reason that it takes 20 minutes between the Earth and Mars to communicate, in short. So the idea is that the reason why this conflict happened is that when C was written, that was before the network partition, but then immediately the network partition happened and C could not propagate to the other nodes. So on one side of the partition, we had value C, And after the network partition, somebody created a version D on the other side of the partition. And that other side of the partition was not informed that there was a value C at 3 o'clock on N1, right? So the version D was created thinking that the last known time was 2 o'clock on N1 with value B, right? Okay. So it's exactly the same thing on Git with what happens if you branch and two people modify their branch independently of each other, then you have a conflict, right? That you need to solve if you want to merge them back.
Okay, so the vector clock is local to the node rather than the complete system.
The vector clock is known to all. So you have the whole vector with all the times on every machine, right? But what happens is that when you create a new value for the vector clock, you increase the value on the node on which you are. So if you are on N1 and the last value was 2 o'clock, then you make it 3 o'clock. Right? So then you have N13 instead of N12. And then that vector clock goes everywhere, right? The vector clock is like a label on the value, right? Every value has the vector clock, and you know what time it was, when was the last time that it was seen by every machine, right? The reason it's a vector is that you actually have one value per machine. It's just that when it's absent, that's 0, basically. But you have a value for every machine. And in the exercise session, you will define, if the exercise is still here, the definition of the relation on vector clocks to compare vector clocks. And here, N13 is after N12. This one is intuitive. And here, D is also after N12 because N12 is in fact N12 and 02, right? Implicitly, the value D. It's N12, N12, N20. And so N12, N20 is smaller than N12, N21, right? That is in the future. Does that make sense? Right? Because it must either stay equal or increase for all the machines when you compare the vector clocks to be in the future. And you see that C and D, so the two vector clocks, cannot be compared because N13 is greater than N12, but N21 is greater than N20. Right? So this is why they don't compare.
Yep.
Right? Does it make sense?
Yep.
You'll have exercises on this, right? There will be exercises where you can formally define the relationship, but really think of it as a DAG. So you have a DAG, just like in Git, you create branches. The vector clocks are nothing else than a labeling mechanism for the DAG, right? It's a way to create the DAG implicitly. For a line, you would use numbers. You would say 1, 2, 3, and so on. But for a DAG, you cannot use numbers because it's not a line. Then you use vectors. Okay? Does it make sense, or did I confuse you even more? Make sense? Okay. And you can ask again even later on the forum, or if anybody else still wants an explanation, you can even ask again now. That's no problem at all, right? So we have these vector clocks that label the nodes of the DAG, and we have a relation that is a partial order from which the DAG basically is built. So we return the two of them to the user, and the user has to do something with that. So we return C and D, and we already merged the two vector clocks because the purpose of the context is to be fed back when you write it back. So it's like the conflict resolution mechanism. So we say these are values C and D, and the merged vector clock is N13 and N21, right? And what happens is that the user, and here that cannot be automated, the user is going to have to solve the conflict. Just to address your question, let's say that it propagates again and all the nodes exchange all of their versions right here, right? So now all the nodes have all the information. So now we even clean a bit up and prune the old versions. So we saw that A and B are obsolete anyway because they're all in the past. So at some point, Dynamo is able to prune and get rid of the old versions after checking that they have become irrelevant. Right? Okay, so now that we have that, the user made up their minds and they decided that after receiving the values C and D, the solution to the conflict is E. right? Of course, it's more complicated than that in real life if you already try to solve conflicts with Git, but to simplify, that's E. So we write it back together with the context that we got from before. That's the merge vector clock that we got. So we send it back the value E with N13 and N21. And then what happens is that N1, because all the network partition is gone and N1 is back, N1 increases the clock, saying, oh, now it's 4 o'clock when I'm writing this new value E. And now I have N1 4, N2 1. Everybody agrees? Right. So now, what happened is that I reconciled this conflict with a vector clock that is in the future of both of the conflicting vector clocks. Right. That's the beauty of a DAG. A DAG, when you have branches, you can merge them back in the future. That's how you get eventual consistency. Right. We have a question over there. Maybe we can throw the microphone. Small hops, not in a single shot, because we don't want to hurt anybody. Small hops, just a few people. Yeah, all the way. Yeah. Okay, go ahead.
In this case, wouldn't it also be enough to take N13 as last resolved version? Because I think when you look at the previous parts of our graph, before the D on the right-hand side, it was N12. So it seems to me that for one key, the version numbers can stay the same. If for another one, you increase them.
So the idea is that the increase happens upon creating a new value, right? So if you take the perspective of N1, for example, N1 has to see a chronology, 1 o'clock, 2 o'clock, 3 o'clock, 4 o'clock. So then you see that there was A, there was B, there was C, and now there is D, right? That's because N1 did the change. So the clock increases. And so if you look here, the 3 increased here as a result of N1 writing the value, and here N2 increased to 1 as a result of N2 creating the value, right? So now, what I imagine that you are saying is here, why did we increase to 4? We could also have said N1 3, N2 1, right? That's essentially what you're saying. We could have done that, right? So it would indeed be that if you strictly mathematically look at the relation, then yes, it would still be in the future of the two, but you wouldn't have this increment, right? You basically would be, you would have an inconsistency because it's N1 that took care of the update, but now N1 has both C and E at 3 o'clock, right? You see what I mean in the design? Mathematically, it wouldn't be incorrect because you would still have the same DAG and the same structure, but the algorithm that gets executed on all the machines says, whenever you write a new value, you increase your clock, right? This is what happens on the machines, right? So I would say that trying to save numbers by not increasing them probably would cost you more lines of codes to do that than to actually just say, okay, I increase the counter whenever I touch the value. Does that make sense?
Thank you.
Yeah, that's how I would think of it. Okay. All right, so we are there. And now we have reconciled, because now how many maximal elements do we have now? 2, 3? 1. And when we have only one maximal element, it's called a maximum, exactly. We have a question over there. Maybe the microphone, yeah.
2 questions. The one, so if I'm understanding this correctly, whenever a node is responsible for an update, that's when it increments the clock. So the reason we had the N21 was because our N1 was offline, therefore N2 had to handle it.
Yes.
So if it had already propagated before the partition, then would the resolution, if you had, for example, N13 and N21, would the resolution then have been trivial?
Yes, because if it had propagated, then you would have had a line with 4 values, right? Because imagine it had propagated, then we would have had C N13, so still that one, but D would then be N13 N21, right? Do you agree? Because then N2 would have created that new value aware of the existence of C, right? So the vector clock would have been N13, N21. Is that clear? Right? And then we wouldn't have any conflicts because then we would have A, B, C, and D on a line, right? Going top down. So then there would have been no conflict in that case. But you could have had a conflict if somebody on the other side, on the side of N1, had then created during the network partition yet another value, right? Does it make sense? Awesome. All right, very good. It's the first year where we have such an intense discussion on vector clocks. This is amazing. Go ahead.
You said that to resolve this conflict, as a user, you have to provide the context. What if you don't have this context? Do you need to do another GET request to get it, or are there any other ways?
The context comes from the GET request.
Oh, okay.
Right?
So
Whenever you receive a value, you get it with a context, and then you can feed it back into the puts.
okay, so basically you first need to do a GET before you do the put in such
Yep.
a scenario.
Exactly.
Okay, thanks.
Yeah. Okay. And then now I have further questions that I want to investigate. Is like, what happened the first time? Like, how do you know if the value already exists or not? If you just want to create it, do you check that it exists or not? So now I want to investigate that, even though nobody asked. If you could, could you make maybe just a note of that also? I'll see if I manage to find all of that. Right. Okay. Any other questions? Okay. Awesome. It's really great because every year the discussions focus on different things, and then I can improve the material even more for the next year on the parts that were discussed like this. All right. And now there is supposed to be a question right here that doesn't appear. Maybe I can retrigger it if I close the presentation. It's right here. So let me connect again. Hoping it's going to work. Okay, so now I have the connection, and I need to re-share the screen right here. And so I want to know, I see some people eagerly already went there because maybe it's in the PDF, the code. I want to see how we are. All right. So the sweet spot here is between 80 and 99. 80 and 99 means that the speed is correct. If everybody got everything, I can accelerate. If more people are below 80, then I can, maybe below 80, then I slow down a little bit, or I do an FAQ the following lecture or week. But now we are good. Okay, very, 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 very good. Okay, so I have 3 follow-ups that we took note of. Okay. So this means that it is the end of this unit right here on cloud storage. It so happens that it is 2:58 p.m., so I'm not going to start and then immediately stop HDFS. So we're going to take a break now. There is, I think, FISCON. Do we have a FISCON representative? So somebody from FISCON might tell you about the conference during the break. And as for me, I will see you in 15 minutes from now. Thank you.